So if the sum is, what's your guess as to what the expected purple value? Sum is x. Expected purple value is?
Maybe x over 2.
X over 2.
Mm-hmm. Yeah, I would say that too.
And your reasoning is?
Well, each of the dice have the same expected value, so the expected value has to add to x.
Okay, interesting. So let's, so we already saw it with 8. We saw 4. 7. What do you think we're going to see?
7 should be 3.5.
Mm-hmm.
How come?
Because you can, you have numbers 1 through 6 can be rolled on the purple die, and then when you average those, you get 3.5.
Okay, yeah. So 7 is the one where we have all of them. What we won't check all of them, but what would you like to check next?
Let's check a small number, like 4.
4, okay.
So we expect 2.
So we're thinking 2. So what are our possibilities? Here we can write them all down.
You can either have 1 and 3, or 2 and 2, or 3 and 1.
Mm-hmm. So there's actually only 3 cases.
And the average of the purple values is indeed 2.
They add up to 6.
Yep.
Divided by 3.
So we get 2. All right.
And maybe a high number like 11.
Okay. Yeah, 11's a good one to check.
So we expect 5.5. So
All right.
we have a small number of cases. We only have 5 and 6, and 6 and 5.
5, 6, 6, 5.
And the average is 5.5.
Yeah,
Yep.
it's 5.5. Okay, so good. So this is a really interesting entire field of probability, I guess, where instead of looking at the general case, you have a restriction. And the restriction sometimes can have a big effect on what the expected value is. So it's always interesting to see these problems and see how that restriction affects the expected value. And for the next segment, we're going to look at a problem we've actually looked at before. I don't know if you'll remember it or not, but it's a really interesting dice expected value problem.
Right.